Okay, limits to non-malleability. So I'm going to talk about non-malleable codes. Let me first explain what they are. This slide is not going to have a formal definition because the actual formal definition we need will be much simpler than that. So as long as you understand the intuition, that's good enough. I'll explain why the actual definition we need is simpler. Okay, so non-malleable code, consider a channel where you encode X. It's not encrypted, it's encoded. Very importantly, there are no secret keys. Everything is public, but possibly randomized. You encode X, and you send it over the channel, and then you decode it. Except in the middle of the channel, there could be a tampering function applied. One requirement is a correctness guarantee, which is very simple and easy to achieve. The requirement is if F equals the identity function, indeed the recovered message is correct. Okay, and I'll talk about security in a minute. Just to contrast it to error-correcting codes, which everybody's used to, in error-correcting codes, we want correctness even if F is not the identity, even if F changes some bits. Here, we don't care. We only care about correctness when F is the identity. However, we do care about something I'll call security, even for other Fs, not just the identity. So the security is this. The received output at the end, X tilde, after you first encode, then apply F, then decode, has to be either correct, equal to the original X, or completely unrelated to the original X. And moreover, this either or should be also independent of X. Okay? So the function could choose to not do anything, or it could choose to change to something unrelated. So things we don't want, these are malleable, is if the function could change an encoding of X to an encoding of X plus 1, or if it could do something like if 0 is encoded, then override it with some constant, whereas if another X is encoded, don't touch, etc. These are things that are not good, that are malleable. Okay, and to formalize this, which is still not the formal thing, this is just for notation, my message will always be of length k, and the code at the end will be of length n, and the function is applied to an n-bit string, right, to the encoded thing. So basically, the way to define it is by a simulator that doesn't see X. The simulator only sees the tampering function F, and it outputs either some constants or some distribution over constants, or it can output the string same, which means I'm not changing anything. And this should be, let's say, statistically close to the output of this experiment. Okay? Or again, another sort of equivalent definition, still not very formal, is that there exists a distribution that depends only on the function. It's a general distribution depending only on the function over the identity function and constant functions that generates this channel. Okay, is this clear on the intuitive level? I'll give a formal definition later, but it's clear what we're doing here? Great, so these are non-malleable codes. I forgot to say they're introduced by Jimbovsky, Piaczek, and Wicks in 2010. First of all, an obvious thing with this definition is that it's impossible to achieve. In general, like easily, I can apply the following function f, which is decode, get x, set x tilde to be something else that's related to x, and re-encode. That's obviously malleable and always possible. Okay, so therefore we cannot protect against arbitrary functions, and we must consider the set of functions, restrict the set of functions we consider. And in particular, the same thing shows that if E and D are efficient, then we cannot protect against P. Right, because decoding, etc., this F is efficient. Okay, so we have to restrict the class F. You're not supposed to read it. I just wanted to impress you with the fact that there are many work. This is not everything. Yeah, so there are many. This is all just from 2010. There's lots and lots of upper bounds in different models. Yeah, good. So there are many results in different models. You can look at the last bullet. Explicit and efficient, existential or probabilistic method, with CRS, information theoretic, computational, etc. On the other hand, there are not many lower bounds. I tried hard to get some lower bounds, but there are not many. The only general lower bound is basically the lower bound I showed you, which is very simple and was in the first paper. And there's another lower bound, blockwise tampering, but it's also very simple. And all the other lower bounds that were considered were either for special types of non-malleable codes, or they talked about the rate and efficiency. There's some lower bounds there. And what we want to focus on is general lower bounds. We want to write theorems of the form, there is no non-malleable code against this class f. So we know there isn't one against the class f of all functions. We know there isn't an efficient one against the class f equals p. We want to do some more, okay? For natural classes f that are motivated by known positive results. So the way I'll present it is I'll talk a little bit about positive results just as motivation for why we chose this class and what the negative result is. But I'll be vague and intuitive and hand-wavy on the positive results because there are many details and I'm going to ignore them and lie about them because I'm only using positive results as motivation. I will be more, I will not lie about the negative results. Okay, so I'm not really lying about anything, but I just don't want to go into detail with the positive results. Okay, and for now, consider only unconditional results. We don't know assumptions. Everything is information theoretic. My last result will be computational, but for now, forget about it. And then when we get to it, we'll talk about it. Oh, I forgot to set my timer. How much time do I have, Tal? 38 minutes. Okay. Good. So this is our goal in this work, is to give results like that. And instead of giving you a list of our results, I'm just going to start with motivation and claim the results. I'll give the whole list together at the end. Any questions so far? Okay, so before giving the result, here is a formal definition. Let me say that our negative results will be for non-malleable codes over 1 bit, encoding 1 bit. This is fine for lower bounds, right? So I don't need to worry about rate. It's even for just k equals 1. And it turns out that for k equals 1, there's a much simpler, this is the definition you should remember. For k equals 1, there's a super simple definition of non-malleable codes, which is equivalent to the general definitions. And the definition is the following. You take 1 bit b. So a code ED is non-malleable against epsilon non-malleable against, let me just say epsilon for positive results, we would like it to be negligible, but in our negative results, it will even be 1 over poly. So a code is, ED is non-malleable against a class F if, for every little f in the class F, if I encode a random bit, either 0 or 1 with probability half, and then I encode it, and then apply f, and then decode it, f will not succeed to flip the bit except with probability half plus epsilon. Okay, so this is an easier definition to work with, and it turns out to be equivalent to the intuition. Do I always decode to either 0 or 1? Let me think if it's important. I think it... Yeah, or it can output something. I think it's fine even if you want to add the null. I don't think it matters. Okay, good. So this is a definition, and now let me start with one motivation for our first result. With the results, this is sort of a warm-up result. It's the simplest result. So first, just recall error-correcting codes. I'm going to set them up as an upper bound for non-malleable codes. So error-correcting codes, there's a code. You can have a code with some distance d, and you can correct up to d over 2 minus 1 symbols. Okay, and there are codes that achieve this. In error correction, you want, I assume you all know, but let me just say, you want correctness whenever you change up to d over 2 minus 1 symbols, and there are no requirements if you change more symbols than that. Okay, and this is tight for a code of size d. I wanted to say this could be viewed as a special case of non-malleable codes. The class is the set of all functions that change the right number of, the right fraction of symbols. This is the class, and indeed, if the class is restricted to this, then I will always output the same, so it's will never flip. Now note that for error-correcting codes in the results that we have, I don't know, read Solomon codes or any error-correcting code that you want. In general, the functions can be arbitrary. You don't need to put any restriction on them. As long as the function doesn't change more than distance d over 2 minus 1 symbols, I can correct it. I don't care what the function was. Now our hope is the following. Non-malleable code is a relaxation on error-correcting code. I don't need correctness. I only need correctness for the identity function. Okay, so it's a much more relaxed setting for correctness. So the hope is maybe we could have non-malleable codes against larger set of functions. So this is the question we want to address. Can we construct non-malleable codes against arbitrary functions that change d over 2 symbols? You see, it's one more than the previous one. I want to note here that all those positive results, they do change a lot of symbols. They could change the entire code word in all the known results. But in all of them, the function is limited in some way, either computationally or which bits it is allowed to look at, etc. So the question is, can we allow arbitrary functions with absolutely no restriction that change d over 2 symbols, one more than possible with error correcting codes? And the answer will be no. Okay, so that's the first result. Oh, and the answer is no for 3 or more messages. If the message space has only 2 messages, actually the answer is yes. But if the message space has 3 or more messages, the answer is no. Okay, so this is the first theorem, which is what I said before. This is impossible. Who is talking? Yeah. Wait, what is the function? Yeah, okay, good. Yeah, this is a lower bound. So for any code you give me, you give me the code ed, I will look at the code space, C. This also, let's assume everything is for 1 bit, because it's an impossibility. I will look at the code space C, and I will find the distance d, which is the smallest distance between any 2 code words. Okay, and I will claim that your code is insecure against, or is malleable against the set of functions which can arbitrarily change up to d over 2 symbols. I'll show you the attack so you'll see the function. Am I not understanding your question, Zvika? Yeah.
You start by a class of adversaries or from a class of encoding functions?
I mean, somehow because there is a D, it's easier for me to state it if you start with your ED and claim that. I'm claiming you cannot come up with a code that takes 1 bit or 1 symbol, if you want, the alphabet doesn't matter, to n bits, such that your code has Hamming distance or Hamming distance D, and yet it is non-malleable against functions that change up to d over 2 of the symbols.
What is the Hamming distance?
Let's say it's bits that... No, the encoding cannot be deterministic.
The whole distribution of 0 words and the whole distribution of 1 word, what is the distance, like the minimal distance between a 0 word?
It's a minimum, so the distance is, if there exists some x such that every encoding of x is d over, at most d, okay, the distance, every 2 code words should be at least d apart. This is a lower bound on what the definition of the distance is. Every 2 code words should be at least d apart. And moreover, it's exactly d if there exists a code word, if there exists an input such that every encoding of that input is d, it has another code word that decodes to something else within d symbols from it. And I'm sorry about what I said about the bit. This is actually not bits because it's for message spaces greater than 2. I'm sorry. This is the only result where it's not true. But for message space equal 2, it is, in fact, there is an upper bound. I can say everything again if I'm confused you, but 1 second, I'll get back to it because somebody else asked something. Yeah. Yeah, it's not small enough. I'll talk about that result. Zvika, let me show the result and then ask again. The proof is very simple. In fact, I intended for this to be a warm-up result. Did somebody else have a question, I thought? Yeah. No, it's not. The result is very simple. However, if the message, if you just encode 1 bit, a simple repetition code, just repeat the bit n times, is non-malleable against functions that can change not only d over 2 symbols, but even d minus 1 symbols. Okay? Maybe this will answer your question, Zvika. This is an example of a non-malleable code. Let's talk about it. Here's an example of a non-malleable code. Your bits are, your message space has 2 things, either 0 or 1. Okay? I'll use a repetition code. I'll repeat 0 n times, or I'll repeat 1 n times. What is my decoding algorithm? Let's say the decoding algorithm, if everything is the same, it decodes correctly. If everything is not the same, it decodes to 0, always. Okay? That's a repetition code. This is non-malleable. Against any function that changes all but one symbol. Any function that changes all but one symbol would either not change anything at all, or would always decode to 0, which is equivalent to setting it to 0. It doesn't matter what was encoded before.
Sure, this example is deterministic, right? I mean, if you want to show a lower bound, you need to work also against randomized, and then there's many encodings of 0.
Right, correct. You are right. This example is a very simple upper bound, and it is deterministic. My lower bound is true even for randomized, yes.
But then the distance between any possible encoding of 0
Yes.
and possible encoding of 1, and any possible encoding of 1 and possible encoding of 2 or something? What is
Yes, you'll see in a second in the proof, okay? Good, so if I have more than 2 messages, I'm claiming that there's no non-malleable code. You cannot do any better than error correcting codes. Here is the proof idea. This maybe answers your question. Here's the proof. So let X star be some input message from the X stars of size K bits, such that every possible encoding of X star is within D over 2 distance from some string that will be decoded to something different than X star. Does that answer your question? Okay, this is my X star, okay? That's the proof. So here is the tampering function. So for whatever encoding scheme you give me, I will build this tampering function. The tampering function will look at the code word, will check whether it happens to be an encoding of X star. If not, it will not touch anything and just do nothing. If it is an encoding of X star, it will change D over 2 symbols so that it's not exactly an encoding of something else, but something that decodes to something else. Okay? And then you can prove, so this is it for the tampering function. I have to prove that this tampering function, in fact, is not the same as overriding with a constant. And this is the case if I have more than 2 messages, which, I don't know, it's easy to show. If I change it to something else, I can take some other Y star, which the tampering function will not touch. And so by correctness, it will always decode to Y star. And I'll show that if it was X star, the message changes to something else that's not Y star, and if it was Y star, it remains Y star. Okay? I can talk more about the proof, but it doesn't matter. But the theorem should be simple enough to understand, so if not, it's my fault and you should ask. Okay. Okay, that's the end of this first one. The second theorem is also fairly simple, and it's about input locality. The definition of input locality, a function has input locality 1 if every input bit affects at most a single output bit. That's the definition of input locality 1. And we showed that there is no non-malleable codes against the class of functions, even if I only want input locality 1.
that just means like you XOR some string there? That tampering is just XOR?
No. Why would XOR work? Maybe you have another proof. I don't know.
One is just, you either keep it the same or you modify it, right?
You either... No, input locality 1 is not the input locality 1 is each input bit influences at most one output bit. It doesn't have to be the same, but in fact our result will be even for the same output bit. I'll say it later. It doesn't have to be the same, but the actual counterexample we give is all the input bits influence the exact same output bit, and all the rest of the output bits are set to constants. That will be our specific counterexample. It could be very complicated function. So the proof was using a similar idea to before, to the codes. Here's the tampering function, but I will not show why it works, why it can be simulated, why it's non-malleable. But the tampering function will look at the code word. It's not that complicated, the function. It just looks at the code word and checks whether the entire code word encodes, let's say, 0. If so, it changes it to some hard-coded different code word C1. If it's not an encoding of 0, it changes it to C2. C1 and C2 are hard-coded values that satisfy the following properties. They're identical to each other except for a single bit. Therefore, this function has input locality 1, because the output will always be the same no matter what, except for one bit where C1 and C2 are different. And yet, the decoding of C1 is different from the decoding of C2. So you can find such C1 and C2 by just doing some walk on the code. For any code, you can find such C1 and C2, and this tampering function will work.
This assumes that if, for example, your D was randomized, and presumably could be even, maybe the distributions will not be identical, but you could imagine that they would have only one statistical distance, DC1, so DC1 could be still very close to DC2.
Good. So about the decoding algorithm, the original, let me just say something about deterministic decoding algorithm. Let me check the time. The original definition had a deterministic, by definition, they just wrote that the decoding algorithm has to be deterministic. I think it's because they thought that this is without loss of generality. In fact, it may or may not be without loss of generality. I do not know. It is, deterministic decoding is without loss of generality for encryption, say. It's not clear that this is the case for non-malleable codes. And so, yeah.
For example, the Hamming distance, like if they have only Hamming distance 1, maybe there will be only difference 1 over n, the distribution is D of C1 and D of C2. So
Right, so we have 3 results. Let me say first what I'm certain of. We have 3 results. One of them works only for deterministic decoding and only for perfect correctness. One of them works for either deterministic or randomized decoding, but for perfect correctness. And one of them works in any case. I think this one indeed requires deterministic decoding, because what you say is correct. I can't hear. DC is the whole code word, yes. Yes, you're talking about output locality. I'm talking about input locality. Input locality is every input bit influences only a single bit in the output. Here, indeed, the output bit depends on all bits of the input. I mean, my output is either C1 or C2. C1 and C2 are identical, except for one bit. Exactly. There's one bit that depends on all the bits of the message. I'll talk next about output locality, which I think is more interesting. Good. So, okay, so let's, yes. I don't assume I prove it, but I just didn't prove it on the slide. But it's not so hard to prove it. Start from 2 code words that are different and do walk towards them by changing one thing at a time. At some point, it will flip between them. These are not necessarily code words. It's just strings that decode to different values. They don't have to be legal code words. In fact, they're not legal code words. Okay, good. So let me contrast input locality with output. This is a lower bound. For output locality, we have known upper bounds that are much more than 1 bit. So in output locality, I gave a more formal definition because I will talk about it a little more. Yep. I can't hear you. Yes. Yes, so I think this is the result that needs both perfect correctness and deterministic decoding. I guess as we look at the proofs, we can figure out which is which. Good. So let me just contrast this with an upper bound of output locality. So a function f is said to have output locality m if every output bit depends on at most m input bits. You cannot have one output bit depending on all input bits, for example. So there are known positive results that give efficient, explicit information theoretical non-malleable code that construct END that is secure against tampering function with output locality n over log n, where n is the whole length of the string. Okay, so this O, maybe it's a specific constant. It's not arbitrary O. Okay, so this is very different. For input locality, we cannot get even input locality 1. For output locality, we can get quite large output locality. Okay, good. So these two results, I sort of view them together. Let me move on to the next result, the next class. So it will be next. I presented it now just to contrast between input locality and output locality. But next I'll present the lower bound. We have a lower bound for, I can tell you it will be n minus log n is the lower bound. So n over log n is possible, n minus log n is not possible. But I want to motivate it from by average case versus non-malleable codes because I think it's a nicer motivation than just the fact that there exists some upper bound. And also it's a good thing to know. This is well known. But notice that if I give you an explicit non-malleable code for some class f, no matter which, any class f, this will give me explicit average case hardness for f. Okay, what does it mean? Just by definition, I guess with the proof we will see what it means average case hardness for f. So if I have non-malleable code, from now on everything is 1 bit. If I have E and D are a 1-bit non-malleable code for f, I will define the following. My hard problem will be D, the coding algorithm. And my hard distribution would be an encoding of a bit, either 0 or 1. Okay, so I claim, what do I claim exactly? I claim that if ED is a non-malleable code for f, then the following is an average case hard problem for f. There's no function in f that can compute this Boolean function d. Cannot compute the Boolean function d when given input sampled according to E of a random b with good correlation. So d is, f is not, d is. Okay, so f is a class of non-Boolean function. F, think parity, for example. I don't know. F takes n bits and gives you maybe 1 bit, right? This is what D does, because I'm encoding 1 bit. E takes 1 bit and gives you n bits. D takes n bits and gives you 1 bit. F has the same input and output size, yes. Okay, no, sorry. The function little f has, here. Let me just say, good. You choose a bit b at random, you encode it, you get n bits, you apply a function f, yes, it goes from n bits to n bits. Okay, I'm claiming that decoding it is hard to do in this class f. So you can, if f has alpha advantage over E of b, let me just write it and then maybe I can answer your question. Good. I want to say that the non-malleable, the fact that, that ED is non-malleable against the class F, okay, means that I cannot find a function in F which can predict, given E of B, where B is random, can predict whether it encoded B or not, whether it encoded 0 or 1, okay? Oh, sorry. So what I want to say is, if F has alpha advantage over EB, then I will get non-malleability. It flips the bit with half plus alpha. So the same advantage I have in the non-malleable code, I have in the hard problem. Okay? Let me see if I said everything that says here. Yeah, good. Okay, so there's like some asterisks. It's not exactly the same class f because my function is not just apply f. I also need to have, the class of function need to be somewhat expressive so that I can have, what is it called? Combinations, composition, so that I could do if-then in the class. Okay, so I can apply f, and if it's 0, then I rewrite with this C1, and else I rewrite with C0. You're trying to go from 1 bit to many bits? That's what bothers you?
No, I think yeah, anyway, I think the family of,
so,
the right-hand side is family of Boolean functions.
Okay, good. So think of, good. So n-to-n functions is, you can think of it as n Boolean functions.
Right,
okay?
Boolean functions, and if the family is closed under negation, I think it works.
And it also need to have if-then, which maybe is the same as closed under negation. I don't know. It also need to be closed under simple if-then, put a constant. It should still be in the family, right? Like this is my tampering function.
If the ith bit of C1 is 1 and C0 is 0, then this is just
I mean, I think the right thing to think about, you all seem confused, I'm sorry. Think of like parity is hard for AC0. Think of something like that. If you don't know what it is, then I don't know what to say. Okay, in terms, I don't have a good example. But this is the positive result, or I don't know, this is one direction. Our result is in the other direction. We want to ask, what about the other direction? We would like classes of circuits that have some average case hardness known, like what I just said. Could we use that to build a non-malleable code for F? I think I'm not doing well at all in time. Okay. 14, oh, maybe it's okay. Okay, so we want to ask about the other direction. Does average case hardness for F implies non-malleability for F? Okay, and the answer, we want it to be yes. It seems to be yes. There's a previously known result that sort of did answer yes, but with lots of caveat. Okay, so there are previous results. Oh, I forgot to name my co-authors. I'm sorry. This is joint work with Marshall Ball and Dana Dachman-Solid, sorry, and Mukul Kulkarni. This work is. And a previous work of ours, plus another previous work of ours with Rachel Lynn, did basically answer this with a yes. We showed a general framework for if you give me any class with some good enough average case hardness and some extra assumptions and some CRS, then we can build a non-malleable code, okay? And we would like to do it without the CRS and without the extra assumptions, etc. That's the question. And there are also explicit construction for specific classes such that AC0, which when you look at the proof, it does use the same proof like, parity is hard for AC0. So it looks promising that there are constructions that rely on average case hardness, and this is what we would like to achieve, but we showed that it's not possible. You cannot do it without any assumptions or CRS. Okay, so our third theorem is about output locality, if that's what you were asking before. I'll restate the theorem again with slightly more parameters, but we basically say you cannot achieve output locality n minus log n. Why is this related to all this average case, etc.? Exactly because parity, so this class of function f, it's the class of function that where each output bit depends on at most n minus log n of the input bits. Okay, that's the class. So you look at every output bit, depends, it doesn't have to be the same n minus log n bits. Okay, this class, you cannot compute parity with probability better than half. I think even intuitively it kind of makes sense. Even if I had n minus 1 locality, you still cannot compute parity. So there is a hard problem for this class, average case hard problem for this class. It's parity, and yet we cannot leverage it to build a non-malleable code for this class. Okay, so the whole average case was just to motivate. The theorem doesn't have anything to do with average case in the statement of the theorem. There's no non-malleable code with output locality n minus log n. And this is the same theorem, but with more parameters. The only difference is I specified the epsilon, which is 1 over 4n. So you cannot achieve non-malleability with distance 1 over 4 to the n. Now, I had a proof for this. Let me think whether to go through it or skip it. 11 minutes. There's one more result after this, but it's the most complicated. Okay, let's see. But this proof is simple. I think maybe it's better to give a simple proof and skip the complicated proof. I don't know, but maybe the more complicated, the more interesting. I don't know. Let's see. So here is the idea of the attack. Let's assume somebody gave me a code, ED, and claimed that it was, or so any code, ED. I want to find a function f, which is n minus log n output local, and yet mauls the code. Okay? So here is what I'll do. I'll say whatever the code is, there are two possible cases. Case 2 is the opposite of case 1, so there are only two possible cases. I'm setting epsilon equal 1 over 4n just because this is what will work out later. So let's assume I encode a bit. I have n bits in the encoding, and then I I set the last log n bits completely at random. What's the probability that now when I apply decoding, the original input will flip? Well, it's either at least half plus epsilon or at most half plus epsilon. These are the two options. And for each separate option, we'll have a different attack. But both of these attacks will have output locality, what I wanted. So in the first case, it means that the decoding will remain the same. No matter if I choose at random the last log n bits randomly, the decoding will remain the same with probability half plus epsilon. Then here is my attack. Here's a function. The function, given input C, will choose the last log n bits at random, and will look only at the first n minus log n bits. It will look at this, and it will decode it. If this decodes to 0, it will rewrite everything with some code word C1. And if it decodes to 1, it will rewrite it with a code word C0. Notice C1 and C0 are hard-coded values that decode to 1 and 0 respectively. Okay, and this is exactly the probability that the code word flips. Remember, this was our definition. The probability that the code word flips is exactly half plus epsilon, just because this is the case I'm handling. And this attack works well. The other case, let me just remind you what the case was. The other case is that it remains the same with probability at most half plus epsilon. In other words, it flips with probability at least half minus epsilon. Okay? But this is still good because why? If it flips with probability half minus epsilon, when I set the last log n bits at random, well, if my random choice happened to be exactly the same, didn't change anything, then I know it will not flip for sure because of correctness, right? So the probability that it flips when I choose them at random, you can divide it into probability that it flips conditioned on it stayed the same, and that probability is 0, plus probability it flips conditioned it didn't stay the same, times that probability, which is 1 over n. So when you do the calculation, it exactly brings it up, and you plug in epsilon equals 1 over 4n, you exactly get that it flips with probability half plus epsilon. In other words, the main idea is this: if it flips with probability half minus epsilon, I will also leverage the correctness to say there is one setting that happens with probability 1 over n where it flips with probability 0. So the rest of the probability is distributed across everything else, and I get my advantage. The numbers work easily. Okay, so this is the same theorem again. Impossibility of non-malleable codes against tampering with output locality n minus log n. Let me just mention, so far I motivated it sort of in two ways. One is it's kind of related to the upper bound, which achieved a positive result for n over log n. Now I have a lower bound for n minus log n. That was one motivation. A second motivation was with average case. This is a function for which there exists. This is separation between average case hardness and non-malleability. This is a class for which there is average case hard functions. And here is a third motivation for why we care about it. Let's say we want to ask, what is the smallest family for which no non-malleable codes exist? Smallest in terms of number of functions. So what do I mean? This goes back to the question I received in the beginning. So the original paper showed an existential result, not an explicit code, an existential result that said for any family f, no matter which, if that family has not too many, but this is quite a large number in fact, but not too many, not all functions, if f is such that the size log f is n minus 2 log 1 over epsilon, then there exists some epsilon non-malleable code. This was the existential result. Notice that the class of all function is something like n plus log 1 over epsilon, something like that. I don't know, n plus log n. Anyway, the specific f prime that we used in our proof, I wrote the proof for epsilon equals 1 over 4n, but the general statement could have 8 over epsilon in there. Our f prime used in the proof has size log f is of the size n minus log 8 over epsilon. So these are kind of pretty close. So I know that for the top number, the green number, there always exists a non-malleable code, and for the bottom number, I found one specific example of a class for which there is no 5 minutes. Okay, this is n minus log 1 times log 1 over epsilon minus 3. Okay, so they're close. This is a third motivation. Good. So I'm done with that. You can now start thinking about computational stuff. So far, everything I talked about was even not taking any efficiency into account. Now let's think about efficiency about computational assumptions. And this is the question we want to address. So I will not go through the proof, but I'll tell you what the result is, which I think is interesting. This is perhaps the most interesting, but the hardest to explain result, because there are many annoying technical subtleties. So it's good that there's no time for them. But let me state the result. So this is the motivation. So we have explicit, efficient, unconditional information theoretic non-malleable codes for various classes, including NC0, AC0. AC0 are like circuits of constant depth. And even for circuits of depth, fan-in2 and depth log n over log n times some constant c. The question is, well, let's try, what about NC1? NC1 are circuits of depth log n. And in fact, if you could do for any O of log n over log n, you will get all of NC1. Can we achieve non-malleable codes against NC1? That's the obvious question, right? NC is like log n, log squared n, etc. There's no hope currently at this point in time. There's no hope to prove unconditionally. Why? Because we don't know how to separate NC1 from P. And I already told you we know easily there are no non-malleable codes for P. So if I could find a non-malleable code for NC1, I would have a separation of NC1 from P, which I guess we believe, but is beyond our reach today. So the question is, could we just assume this? Could we assume the minimal assumption? So if we had a non-malleable code for NC1, that would necessarily give some average case hardness for P, just the same way I said before. So the question is, could we just assume it? Let's assume there is a language in P that's computable in polynomial time, and there is a distribution such that this distribution is hard for NC1, even though it's easy for P. I'll just assume that they're different. Can I build a non-malleable code from that? And for this, we also proved that the answer is no. Here, this is the same question written again. Oh, let me say first why maybe yes. In fact, we do give such an non-malleable code for 1 bit, so we do give it, but it uses CRS and it also uses other assumptions. Okay? And the question is, can we do it without a CRS? And the answer is no. And since it's computational, we can't just say no, so it's no under black box reductions. Okay? Good. So that's the statement. There is some more interesting stuff to the statement because it's much harder to define what black box reductions are for something like NC1. There are difficulties that come up that don't come up, when you talk about P, about polynomial time. So we have to define black box reductions for this fine-grained setting. Okay, so here's the theorem. The theorem is stated not for NC1, but for general class F, but we can instantiate it with NC1 or with NC. So the theorem is non-malleable codes are impossible. It's impossible to build a non-malleable code against a tampering class F by only using, in a black box way, the assumption that there is some hard problem for F. Okay, so this is the statement. I have a lot of slides that I'll skip. I want to get to the main point, but we can instantiate it with NC or with NC1. And this statement is not formal. There are extra requirements on F, and those extra requirements are mostly about composition. Okay, like for example, definitely that it's, I wanted to say that it's closed under composition, but that's not a requirement. I'll show you the requirement. Because, NC1, for example, is not. But we can instantiate it with NC1. Okay, so let me say something about this slide. So how to define, I just want to say it's a little hard to define. So what is a black box reduction? I have some proof, R, that has a hard problem. Psi is a distribution, and L is the language. I assume that it's hard for the class F. I will I will say if you can if you have a function that tampers with ED successfully, then I can break this assumption. So we need two things. We need that the reduction is black box, namely given a tampering function A, R to the A, R with oracle access to A breaks the underlying assumption. The important point about point 1 is therefore it should work for any A, even for strong A's, not only for A's in the class, because it's black box. And the second point, this is the harder part, is we want a contradiction at the end. We will say this is how the proof will go. If A was in the class, then R to the A will break the assumption. But if R to the A is not, R with oracle access to A is not in the class, then there's no contradiction. So we need this type of closure, okay, which is hard. In P, it's obvious, so people don't say it. If you have a scheme in P and you have Oracle access to P, you're still in P. But for example, if you talk about depth, it's not necessarily clear. Okay, so we define, and there are many subtleties because we talk about security about when you call the instance, do you use the same security parameter or not? And we have various subtleties there, which I will skip. I will skip those. Yeah, so there's lots of subtleties there, but there is, good. There is a negative result. I wanted to point out where a negative result falls short. The next slide is summary. I wanted to point out where a negative result doesn't hold. So I didn't show you the proof, but it doesn't hold for these cases, and I'm pointing it out because it might be interesting to try to build non-malleable codes for NC1 with this. So for example, it doesn't, we cannot instantiate it when you want to prove, for example, you want to build non-malleable code for NC1, assuming that, for example, NC2 is not equal to P. This, our lower bound doesn't preclude. And also, it does not preclude the building a non-malleable code for incompressibility. Incompressibility is very important because it was used in the same previous works. I said before, there's an L missing there, it's with Rachel Lynn, the 19. It was used before to build non-malleable codes for specific classes. So what is incompressibility? It's a stronger assumption than saying it's average case hard. Incompressibility says not only can't you find a function in the class that computes good correlation with this function, in fact, you cannot even, in the class, you cannot even compress the input to something shorter that later could be used with an unbounded function to compute the output. So it's a stronger assumption, which has been used in previous work, and we do not know how to prevent. So maybe there's hope for positive results there. Good, so this is just a repeat of the 4 theorems, which is good for questions, I think.